In this video, let's look at the NMR multiplicity pattern or the splitting pattern. That is how the spins of adjacent non-equivalent nuclei split when they find themselves in different environments. So let's have a look at this. So this is the splitting pattern that occurs in NMR spectroscopy. So you can have a singlet where there is no splitting pattern. We can have doublet where a particular signal has been divided into two splits. We can have triplet where the particular signal has been divided into three splits. Now the intensities of these peaks, sub-peaks, are what we call the intensity ratios, are determined by the Pascal's triangle. So we have a singlet, it has just one long peak. When you have a doublet, it has just two long peaks which are of the same height. When you have triplet, you have three peaks, of which the terminal ones are the same, then the middle one is going to be longer. So these intensities are determined by what we call the Pascal's triangle. You don't have to keep these intensities in your mind. There is an easy way of memorizing the intensity ratios of the peaks or the splits in NMR signal. Now let's look at something. So this is how Pascal's triangle look like. It starts with figure 1. The next one is 1, 1. The first one is the intensity ratio of a typical singlet splitting pattern. Then this 1, 1 is the intensity ratio of a typical doublet splitting pattern. So when I take this doublet, means the ratio or the ratio of the intensities of the peaks are the same, which is depicted by the Pascal's triangle, where we have 1, 1. The next one, you are going to add these two values. So 1 plus 1 here is 2. You know the ends are always 1 and 1. That means when I take a typical triplet splitting pattern, this is its intensity ratio, where the middle one is going to have a double in height as compared to the terminal one. So this is how a triplet look like, and this is the intensity ratio of a typical triplet splitting pattern in NMR spectrogram. The next one is that of a quartet. So when I have 1, 2, 3, you are going to add these two values. You are going to have 3 in the middle here. Then this one, if you add them, you have 3 in the middle here. Then always the ends are always 1, 1. So these are the intensity ratio of a typical quartet splitting pattern. So for a quartet, we expect to have two middle heights of the same intensity. Then the ends are just 1, 1, also having the same intensity. That is the intensity ratio for a typical quartet splitting pattern. The next one, if you have a quintet, you are going to add these two, 3 plus 3, you are going to have 6. Then 3 plus 1 here is going to be 4. Then you have 1 plus 3 here is going to be 4. Then the ends are always 1 and 1. So that's the intensity ratio of a typical quintet splitting pattern in NMR spectrogram. So for NMR spectrogram, having a quintet splitting pattern, we expect the middle one to be of a higher height as seen here. So this is the 6th. Then the ends here are the 4. And these ones are the 1. So that's the splitting pattern or the intensity ratio of a typical quintet splitting pattern. Now when you come next, so this is quintet. This is quintet. The next one is that of a sextet, where we have 6 splits. So we are going to add these values. So 4 plus 6 here, we're going to have 10. 6 plus 4 here, we're going to have 10. Then 4 plus 1 here, you're going to have 5. Then 4 plus 1, you're going to have 5. Then the ends are always 1, 1, as I said earlier. So the intensity is for a typical sextet splitting pattern. That means for a sextet splitting pattern, you must have two middle peaks having the same height. It is into 6 splits. That's why we call it sextet. So these ones are the 10th. Then this one and this one are the 5. The terminal ones are the 1. That is the splitting pattern for a typical sextet. Then the next one is that of a septet, where we have 1 plus 5. We're going to have here some 6. Have 5 plus 10 here is 15. You can have 10 plus 10 here is 20. You can have 10 plus 5 here is 15. Then 5 plus 1 6. You can have terminal 1, 1. This is a typical intensity ratio pattern for septet. That is an NMR signal which has 7 divisions or 7 splits. In our case, the middle one is going to be the tallest, which is 20. This one. The next to the tallest is the 15, which have the same height. This one has the same height. Then we have the 6, 6, we also have the same height. These ones. then the terminal one at the 1, 1. So that's how you can easily deduce the intensity ratios of the various splitting patterns in NMR signal. This is called Pascal's triangle. I know you might have come across it in your various secondary schools or even your colleges. Now let's see. Now before we proceed, let's understand something. Let's understand what is meant by chemical shifts of an NMR spectrogram. So what do you mean by when you say chemical shift of an NMR spectrum? Chemical shift. So when we say chemical shift, the chemical shift is basically the coordinates on the x-axis in an NMR spectrum. So NMR spectrum displays, let's say, a graph of the intensities of the peaks against what we call the chemical shift. The chemical shift is displayed on the x-axis, whereas the intensities or the height of the peak is displayed on the y-axis. So the chemical shift is just a ratio of the frequency of the nuclei, so the nuclear frequency over the frequency of the spectrometer. So we have the spectrometer's frequency over the nuclear frequency. This is how it is being aligned. The lowest value of the chemical shift moves from the y end or the right end to the left end. So here the lowest value is always here. We have 0. Then the highest chemical shift, which is always a value around, let's say 10, 13, or 14, is always found at this side. That means if you move towards this direction, we increase chemical shift. The nuclei found at the lowest chemical shifts are said to display a signal at what we call upfield. So upfield is a region of the lower chemical shifts. Now from this relation, you can see that if the frequency of the nuclei is smaller, then the chemical shift also will become smaller. That means the region where the nuclei have a lower NMR frequency will have a lower chemical shift. That means that nuclei which is more shielded will display a signal also at upfield, because shielded nuclei which has a higher induced magnetic field and allow a small magnetic strength to enter the nucleus will be more shielded. In that case, it will have a smaller nucleus or smaller frequency of NMR and smaller chemical shift. So a shielded nuclei also display a signal at what upfield, and the upfield position is the region where we have a lower chemical shift. Once again, the region of a higher chemical shift is called the downfield. So the downfield is the region where we have a larger chemical shift value. And this region is where we have the deshielded nuclei. So the deshielded nuclei is a nuclei which has a lower electron density or a lower induced magnetic field that can repel the external magnet that tends to enter the nucleus. So a region of a higher frequency or a higher chemical shift is always shown at what downfield, where the nuclei which is more deshielded will display a signal. So as we move from this direction towards this end, we say we increase the magnetic field, we increase the chemical shift of the nuclei. So let's say we have this compound. So let's say we have alcohol. Let's say we have CH3, we have CH2, then we have OH. This compound has 3 different environments for protons. So we have in proton NMR, this compound have 3 different environments. So we can have proton found on the oxygen, the protons on the middle carbon, then the one on the terminal carbon. So where will each of these protons display a signal in an NMR spectrum? Now this proton, the first one, is more closer to the oxygen because this oxygen is highly electronegative. It will deshield this proton more. So that means this proton, let's say if this proton is A, will display a signal at the most downfield because it is going to be more deshielded by this oxygen, which is more closer to the nuclei than any of these protons. So this proton A will display a signal at what? The most downfield. The middle protons, which is having just 2, is much closer to the oxygen than this one. So this proton too is going to be more deshielded than this. But comparing if here's A, comparing B and A, the B is going to be more shielded than A, but the same B is going to be more deshielded than C because the C is more distant from this oxygen. So the next signal which is displayed in this spectrum is going to be that of the B. The B will display a signal at the next downfield position. Then since this C is having, or let's say is more distant from this oxygen, it will display a signal at the most upfield. So it will have a signal somewhere here. Now, what account for the ability of a signal to display a signal at downfield or upfield? Remember, when we take every nuclei, we have the spins of the nuclei moving in any position haphazardly. So based on the principle of the NMR, when you subject this one with an external magnetic field, so you see an external magnetic field subjected to this nuclei, we expect this magnetic field to create two states within the nuclei. So that difference in barrier, which is the beta state and the alpha state, is what we call B naught. And this B naught is going to be the magnetic field strength. That means that for this particular nuclei, let's say this nuclei A, if it is more deshielded, it will allow more of the magnetic field here to create a greater gap between the alpha state and the beta state. The beta state and the alpha state are the two states which is created in the nuclei. So if it is more deshielded, this barrier, which is called the B naught, the magnetic field strength is going to be higher. That means when you subject this one with a radio wave, radio frequency, we are going to have a higher energy barrier from the alpha state to the beta state. In that case, the NMR frequency will be lost after the flip-flop is going to be of a higher frequency. So if the nuclei is more deshielded, it will have a higher NMR frequency. That means it will equally have what? A higher chemical shift. So if the frequency of the nuclei absorbed is higher, it will have what? A higher chemical shift. So taking these three nuclei, since this A is more deshielded, it will allow in a greater amount of magnetic field to create two barriers A and B. That is the alpha state and the beta state. In that case, we're going to have a higher absorbed radio frequency, which will lead to what? Emission of higher NMR frequency. So that's what creates the different positions or different chemical shifts in what? The NMR spectrogram. Now let's look at this same compound, ethanol, which has three different hydrogen positions from A to B, A, B, and C. Each of these protons are in different environment, for that matter, they have their own magnetic field direction. If I take the position 3, that is what? The C. This A here have its own magnetic field in a particular direction. If any nuclei which is closer to this hydrogen has a magnetic field that can oppose the direction of this position, it can cause a splitting of the signal displayed by the C. So this C has its own direction of magnetic field. If there is any other adjacent nuclei that can interfere with this magnetic field, either in the same direction or in opposite direction, it can cause splitting of the nuclei displayed by, let's say, the C. So if the nuclei which can split this, we see the nuclei which are in different position or in different chemical environment but adjacent. If their field or their spins opposes the spin of your reference, or let's say nuclei of reference, it can cause splitting or division of the signal displayed by your nuclei of reference. So in this case, if a signal is displayed by the position C, what happens is if there is any adjacent nuclei to the C, it will divide the signals of what? The C. If only the adjacent nuclei is in different chemical environment. So in that case, the magnetic field of the C and the B are going to interact. So the interaction is called coupling, and the division of the signal into sub or multiplicities is what we mean by what? Splitting. So let's focus on how the splitting pattern is derived, or how to draw a splitting pattern for a particular position. As we said earlier, if the signal displays just one signal, that is, has no splitting, we call it singlet. If it has two splits, we call it doublet. If it has three splits, we call it triplets. If it has four, quartet, quintet, sextet, and what septet. And these are what we call the intensity ratios here. So here's 1, here's 1, 1, here's 1, 2, 1, as we displayed earlier by the Pascal's triangle. So let's see how we can deduce a particular splitting pattern or the multiplicity pattern of a particular nuclei in a compound. So let's start with our compound. Let's say we have ethyl bromide. So you have CH3, we have CH2, then we have what? Br. Now, what is the splitting pattern of the different hydrogen environment we have in this compound? Before then, we have what we call an N plus 1 rule. N plus 1 rule. This rule is what helps us to determine the number of splits or the splitting pattern of a particular nuclei of reference, where this N represents the number of the adjacent nuclei that can interfere with the magnetic field of the nuclei of interest. Now, if I take this compound Ca3 CH2Br, this compound will display two signals in NMR spectrogram. So we have the first signal displayed by this. We have the next signal displayed by this. Now, once again, these two hydrogens, we said they are in the same environment. Therefore, each of them will display or they will emit the same frequency of NMR. And for a same spectrometer, we expect them to have the same chemical shift. In that case, these two hydrogens will all contribute to a particular signal. Now, when I take, let's say, a signal of this hydrogen displayed here, like this, because we have two hydrogens contributing to this signal, that is, they having the same chemical shift, we have what we call the intensity or the integration value of this signal. And that integration value or the integral value is the number of the contributing nuclei for a signal. So for such a signal A here, the integration value is going to be 2 hydrogens. That is the number of the contributing nuclei for a particular signal. Now, what is the splitting pattern of these compounds? When I take A, this A is adjacent to this hydrogen here at position A, is adjacent to this hydrogen. So as shown here, it is clear that this hydrogen, that is one of our reference, and these ones are adjacent. So if here is B and here is A, the splitting pattern for hydrogen A is going to be N plus 1. So the N here represents the number of the adjacent hydrogen to A. When I take this A, we have 3 hydrogens that are adjacent to the position A. In that case, for the A, it will have a splitting pattern of 3 plus 1, where this 3 is the adjacent hydrogens to A. This is what the B. The B is the adjacent hydrogens to A. That means the splitting pattern of A is going to be what? 4 splits, which is what? Quartet. Quartet. So if you have 4 splits, it is called what? Quartet. That means in the NMR spectrum, the signal for the A will look like what? The quartet. Let's look at the splitting pattern of the B. Now this B is having 2 adjacent hydrogens. That is what the hydrogens on position A. So we have what? 2 plus 1, where these 2 is the number of the adjacent hydrogens. Then the 1 is the one in what? The N plus 1 rule. So we have what? 3 splits. So the splitting pattern for position B is going to be what? Triplet. Triplets, because you are going to have 3 subdivisions. Triplet. That's pattern of splitting for position B. Let's take different example. Let's say you have this compound. We have OH. Now, how many signals will this compound display? So we have for proton NMR, we have the proton here 1, we have the ones here 2, we have the ones here 3, then we have the ones at the terminal here 4. So we have 4 signals for such a compound. That is what? Propanol. Now, what is the splitting pattern for the positions? So let's say we have the positions numbered from A. Here's A, this is B, this is C, and this is D. What is the splitting pattern for each of these positions as shown here? So position A, we can see that from the n+1 rule, the only adjacent hydrogens to position A are the ones at carbon B. So we have 2 carbons on position B, and these 2 carbons are what are adjacent to A. In that case, the pattern of splitting for A is going to be 2 plus 1. That's from the n+1 rule, where these 2 are the adjacent hydrogens that are the ones found on what? The B. So we have 3. That is, the splitting pattern of A is going to be triplet. Now what of B? Pause the video and try your hands on. What is the pattern of splitting for position B? Okay, so for the B, the number of adjacent hydrogens to position B are the ones found on what? A and C. So we have 3 hydrogens on position A and 2 hydrogens at position what? C. So we have adjacent hydrogens to be 5. Then plus 1. That means going to give us what? 6. The pattern of splitting for position B is what? Sextet. Sextet. How will C also look like? Now when I take this position C, the adjacent atoms to this position C are the carbon at position B and this oxygen. This oxygen is adjacent to position C and it bears 1 hydrogen. So this hydrogen 2 can equally split the hydrogens at position C, because for splitting of 2 okay, the hydrogens must just be 3 bond distant. So you can have 1 hydrogen on the oxygen which can split the hydrogens at position C, then 2 hydrogens at position B which can split the hydrogens on what? Position C. So all these ones can split the signals at position C. In that case, the adjacent nuclei or the adjacent hydrogens of C is going to be 1 plus 2. So we have 3 plus 1, where this 3 is what? 1 on position D, then the 2 on what? Position B. In that case, the pattern of splitting position C is going to be quartet. Now let's look at D. Now for the D, the only adjacent hydrogen that can split the D is the ones on C. So the C has 2 hydrogens. So you're going to have 2 plus 1 for position for what? D, which is going to give us what? 3. Triplet. Triplet. Now let's bring our idea of the chemical shift to these signals. Let's say this compound displays these 4 signals in an NMR spectrogram. If you are to arrange them in order of increasing chemical shift, we said earlier that if the compound is more shielded, it will have a lower chemical shift. If it is more deshielded, it will have what? A higher chemical shift. So if I move an arrow from D to A, am I going to increase chemical shifts or I will decrease chemical shifts? Now this A is the most shielded in this compound, so it will have what? The smallest of the chemical shifts. Then the D is the most deshielded, since it will have what? The highest of the chemical shift. So if I move from D to A, I'm going to decrease chemical shift. If I move from A to D, I'm going to increase chemical shift. So take note. If you are to show the signals displayed by each of these in NMR spectrogram, so let me see if I can try this. So when I have, let's say this is the spectrogram, the A is going to be the most going to be at the most upfield because the most shielded of all. And since the A is triplet, its signal is going to be something like this at the most upfield position. The next one is B, which is having what? 6 splits, sextet. It also comes So we are going to have 1, 2, 3, 4, 5, then 6. That is 6 splits for B. So this is A, this is B. Then for the C, we are going to have quartet. So the quartet is going to look like this. So we have something like this. That is for the C. Then the D, which is triplet, will appear most downfield, like that. So that's how it's going to be in the NMR spectrogram. Let's try a last example. Let's say I have this compound. So let's say I have over here is ketone. Then I extend here to, let's say, something like this. Let me make it a typical symmetrical compound. Then, how many signals will this compound display in the first place? I have 1, 2, 3. 1, 2, 3. I think that's not the compound I want. So let me erase this end. So I have 1, 2, 3. I have 1, 2, 3, 4, 5, 6, 7. Okay, you have this compound. How many signals will this compound display in a proton NMR spectrogram? Now, this compound is a typical symmetrical compound in which the left side of the ketone and the right side are the same. So in this compound, we have only 3 environments for proton NMR. We have only 3 environments for proton NMR. This environment A and this environment here will display the same signal in an NMR spectrogram. This environment and this environment will display the same signal in proton NMR. The same way, this environment and this environment will display the same signal in proton NMR. So for this compound, we expect to get 3 signals in proton NMR. Now, how will they differ in terms of chemical shapes? So from this orientation, we can see that the C is the most closest to the oxygen. So this C will display the most downfield signal because it is going to be the most shielded. The next one is going to be the B, then the final is going to be the A. So the A is going to be the most shielded among these 3 environments. Now, what is the splitting pattern of each of these positions? So let's take the A. The A. When I take the A, this A position and this other A position are the same. So all the adjacent hydrogens at each side will equally split the signal displayed by this A position. So when I take this A position, this side is adjacent to the hydrogens found on the B. Equally, this side is adjacent to the hydrogens found on the B. So for the signal A, the adjacent hydrogens to a signal displayed by the A are the 2 hydrogens found at this B position, then the one found at this B position. So we have 2 hydrogens here, then 2 hydrogens here. So the number of adjacent hydrogens to the signal A is going to be what? 4 plus 1. So the splitting pattern of A is going to be what? Quintet, that is 5 splits. Now, how will the B look like? So let's take the B. Let's take the B. So the B is splitted by the hydrogens on both A and C. Both A and C. So when I take this B, I have 3 hydrogens here and 2 hydrogens here. That can split the B position. When I take this B, I have 3 hydrogens here at position A and 2 at position C. So I'm going to have an equivalent of 10 adjacent hydrogens to position what? B. In that case, the splitting pattern of B is going to be 10 plus 1, which is 11. Now, any value which goes beyond the 7, which is the maximum, is called a multiplet. So the pattern of splitting for B is going to be called what? Multiplet. So from 8, 9, 10 and above, we call that pattern of splitting multiplet. So the pattern of splitting of B is called what? Multiplet. Let's take C and look like. So for C, it is going to be split by the hydrogens at position B alone. So I have 2 hydrogens here and 2 hydrogens here, which are adjacent to the ones found on position C. So we see you're going to have 4 plus 1, which is going to be what? 5, just like the quintet which you found for the A. That is the pattern of splitting for the C. Now there's one other term I want to introduce. Let's say I have this compound. Let's say I have this compound, and this compound is Br, as we saw earlier. Then I want the pattern of splitting for the position, this position. Now this position has 2 adjacent environments, that is this side and this side. So how would the pattern of splitting look like? I'm going to have 3 hydrogens here, then 2 hydrogens here, which is going to give me 5 plus 1, which is what? 6. So this pattern of splitting is called sextet or a sextet. That is with respect to this position. So this is sextet, or it can also be called this way. This position is split by this end here, by 3 hydrogens. So for this end alone, we are going to have what? 4. That is what? 3 here plus the 1, which is what? That's 4. 4 split. When I come to this end, this position also splits this position of reference into 3, because we have 2 hydrogens here. So the 2 plus this position is going to be 3. So this same sextet can be called quartet of triplet. In this case, you can call it quartet of triplet. So such a compound, its splitting pattern is either sextet or it can be called quartet of triplet. So we normally read from the left side, quartet of triplet. So whether you call it quartet of triplet or sextet, those becomes what? The splitting pattern of this position. Thanks for watching. Don't forget to subscribe to watching so you can receive our next update video on chemical shift. Thank you.